Welcome to this video about algorithms. An algorithm is a systematic approach to solving problems through clearly defined, ordered steps that a computer can execute to achieve a specific outcome. Think of it like a recipe for cooking. Just as a recipe provides step-by-step instructions to make a dish, an algorithm provides step-by-step instructions to solve a problem. Algorithms are everywhere in technology, from search engines to social media recommendations, and they are fundamental to how computers work. Every good algorithm must have four key characteristics. First, it must be finite, meaning it must terminate after a specific number of steps and cannot run forever. Second, it must be definite, meaning each step must be clearly defined and unambiguous with no room for confusion. Third, it requires input, which can be 0 or more inputs needed to solve the problem. And fourth, it must produce output, generating one or more results after processing the inputs. These characteristics ensure that an algorithm is reliable and can be understood and implemented by anyone. Designing an algorithm involves four main steps. First, understand the problem by analyzing the inputs, outputs, and any constraints clearly. Second, select data structures that are appropriate for organizing and managing the data efficiently. Third, design the algorithm by developing a step-by-step solution procedure to solve the problem. And fourth, analyze and optimize by evaluating the efficiency of your solution and improving its performance where possible. Following these steps ensures you create effective and efficient algorithms. After designing your algorithm, you move into the implementation and testing phases. First comes coding, where you translate your algorithm into executable program code using a programming language. Then comes documentation, where you record the steps, logic, and usage instructions for future reference. Next is testing, where you verify that the algorithm works correctly with various test cases and different types of data. Finally, debugging involves identifying and fixing any errors or unexpected behavior in the code. These phases ensure your algorithm is not only correct, but also reliable and maintainable. Once an algorithm is deployed, it requires ongoing maintenance and optimization. Monitoring involves tracking system performance and gathering user feedback for potential improvements. When issues arise, bug fixes address and resolve problems discovered during usage. Enhancement means adding new features and improving functionality based on new requirements. And performance optimization focuses on improving speed, reducing memory usage, and making the algorithm more scalable. This continuous cycle keeps your algorithm running efficiently and effectively over time. Proper documentation of an algorithm is essential for its use and maintenance. First, include a description that explains the algorithm's purpose, what inputs it takes, what outputs it produces, and how it solves the problem. Second, provide pseudocode, which is the step-by-step logic written in plain language independent of any programming language. Third, include examples with sample inputs and expected outputs to show how the algorithm behaves. And fourth, include complexity analysis that documents the time and space complexity using big O notation. Good documentation makes algorithms easier to understand and maintain. Pseudocode is a simplified way to write algorithms using plain English-like syntax. In this example, we have an algorithm called find maximum that takes an array as input and returns the maximum value in that array. It starts by assuming the first element is the maximum. Then it loops through each element in the array and compares it with the current maximum. If an element is greater than the maximum, it updates the maximum. Finally, it returns the maximum value found. This pseudocode is clear and can be translated into any programming language. Understanding the efficiency of an algorithm is crucial, and we measure this using big O notation. Constant time, denoted O of 1, is the fastest and runs in the same time regardless of input size. Logarithmic time, O of log n, is very efficient for large inputs and is used in binary search. Linear time, O of n, grows proportional to the input size and is common in simple loops. Quadratic time, O of n squared, uses nested loops and becomes slower as input size increases. Exponential time, O of 2 to the power of n, is the slowest and becomes impractical for large inputs. Choosing an algorithm with better complexity is key to solving problems efficiently. Let me introduce some common algorithms used in computer science. Binary search efficiently finds a value in a sorted array by repeatedly dividing the search space in half. With a complexity of O of log n, merge sort divides an array into halves, sorts them recursively, then merges the sorted subarrays. With a complexity of O of n log n, bubble, sort repeatedly swaps adjacent elements if they are in the wrong order, with a complexity of O of n squared. And linear search sequentially checks each element until finding the target or reaching the end of the list. With a complexity of O of n, each algorithm has different trade-offs in terms of efficiency and use cases. When designing and implementing algorithms, follow these best practices. First, validate input by checking that all inputs are valid before processing to prevent errors and unexpected behavior. Second, keep it simple by writing clear and readable code that is easy to understand and maintain for yourself and others. Third, test thoroughly using edge cases and boundary tests to ensure your algorithm is reliable and handles all situations. And finally, comment code by documenting complex logic with clear comments for future reference. Following these practices ensures your algorithms are robust, maintainable, and reliable for production use.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.